Welcome to day 7, rational functions. We're going to graph and write equations of rational functions, noting all important features. So before we even get into what rational functions are, let's talk about just graphing in general. So we're going to draw these graphs of rational functions because this is what they're going to look like. We're going to play by the rules of the game. So the rules of the game is that you can only draw a graph through the x-axis or y-axis if there's a plotted point there. So these big old dots. There's a horizontal. If there's a horizontal asymptote, that's what these dashed horizontal lines are. Then both ends of the graph are going to level off to that horizontal asymptote. And a graph is not allowed to cross a vertical asymptote. It will only get very close to it but never cross it. And if I have a vertical asymptote, the graph is either going to go up forever or down forever next to the vertical asymptote. Okay, so right now what we have, we only have been given only intercepts and asymptotes. That's all we have so far. So if you look at this graph, we have a VA here, a VA here. We have HAs, they're the same on both sides. VAs, VAs, HAs here. And if I have a horizontal asymptote, that means I'm going to be level. We're going to be level here. We might be level above it or level below it, but we're going to be level. We got to get more and more towards that horizontal line. So let's see what we got here. Let's play by the rules of the game. So I have 3 pieces of this graph. A left piece, a center piece, and a right piece. Because the VA I'm not allowed to cross. So it is just one graph, but it's got 3 parts to it. 3 little branches to it. Left, center, and right. Okay, so let's do the easiest part. Let's do the center part. I'm going to use black. Well, I have to go through these dots here in the middle. So the only way I can do that, and I got to get, when I get next to the vertical asymptote, I got to go up forever, down forever. So I'm going to go left to right. I'm going to go from negative infinity, x-intercept, y-intercept, up to positive infinity. I can't come back down and make it like a U shape because I cannot cross the x-axis again unless there's a dot there. Let's do the right side next. The right side, I have to be level. You see where I have to be level here? So, see, I have to get closer to this horizontal asymptote being level. So I have to be above the horizontal asymptote or below the horizontal asymptote. I'm going to choose the lower side because there is a dot there. So I'm going to go from negative infinity through the x-intercept and make it level to the horizontal asymptote. Again, next to the vertical asymptote, I have to be either going up forever or down forever. And this last part, it's like, well, there's no dot for me to go through. Well, actually, there's only one thing you can do. The only thing you can do is draw in the upper half here, because I cannot go through x-axis. There's no dot to go through. And this is what the graph looks like. And if you look at it, I have, I'm going to pick pink. I'm level on the left. I'm going up to infinity next to the VA. On the other side of the VA, I'm at negative infinity, going through the x-intercept and the y-intercept, all the way up to positive infinity, and in the center part. And on this right piece of the graph, I'm at negative infinity next to the vertical asymptote, and I'm leveling off again at the horizontal asymptote, going through that x-intercept. So this is what's going to happen. We're going to draw graphs given x and y intercepts, HAs and VAs, and we're going to draw graphs that look like this very segmented type of graphs. Let's do the same thing for the next one. Let's do the center part. Well, the center part, I have to go through these intercepts. So I'm actually going to go x-intercept, y-intercept, back up to x-intercept, and go all the way up to infinity. Maybe inside we have a nice little U shape. And again, there are no dots here. There are no dots here. That means if there's no dots, I cannot go through the x-axis unless there's a dot there. So that means I must be something like this, level going down to infinity, negative infinity, and level and going down to negative infinity again. These are all possible graphs. Again, let's prove what I have. Next to the VA, this side is going down to negative infinity, this side is going up to infinity, this side is going up to infinity, and this side is going down to negative infinity. So that's what's going on with the graphs that we're going to draw today. So let's put some words to all this. We've been doing vertical asymptotes, shorthand VA. It is a brick wall. I cannot cross a VA. Okay? But on either side of a vertical asymptote, you see the graph is either going up or down to negative infinity. So that's what this is here, using the limit notation. That says as x get closer to a from the left side or the right side, the graph is either going up to infinity or down to negative infinity. So on either side of a VA, the graph goes to either positive infinity or negative infinity every single time. It's never going to stop at some specific number. It's just going to keep on going up and up and up, or down and down and down. A horizontal asymptote is a little bit different. A horizontal asymptote just means the ends level off to some y number. It could be -5, it could be 0, it could be 2, it could be any y value. But you can cross in the middle. A horizontal asymptote only means the end levels. It has nothing to do with the middle. What does it mean? Well, this is a notation that says the farther you go left or right, you're getting closer to y equals some number. So the farther left or right that you go, the graph levels off to y equals some specific number. I could draw a little example of this. Something like this. I'm going to just draw a simple one. Here's a VA. Here's an HA. I could draw something like this. Level down to negative infinity, level on the left down to negative infinity, and level on the right up to positive infinity next to the VA. Something like that. That's what they do. So what is a polynomial function? Well, a polynomial function is an extension of what we learned yesterday. It's just a ratio of two polynomials. That's what a rational function is. I'm going to have a polynomial divided by a polynomial, and we talked about what that means yesterday. So what do I need to draw a rational function? Well, what did we do on the other page? All we needed were intercepts and asymptotes. That's all I needed. I needed x and y intercepts and vertical and horizontal asymptotes. So those are the four key features we're going to talk about today. Well, feature number one, a y-intercept. How do you find a y-intercept for the rest of your life? You use x equals 0. So all I'm going to do is find f of 0 by plugging 0 in there. So you could see that I plug 0 into the numerator and denominator for all the x's, and I get -3 over -10, which is just 3/10. So my y-intercept is 0, 3 over 10. That's just some dot on the graph. Well, how do we find x-intercepts? Well, x-intercepts, I have x-intercepts when the whole value is equal 0, when y equals 0. But y equals 0 when I have 0 divided by a number. So basically it's when my numerator is equal to 0. So I have to take my numerator over here, just my numerator. I'm going to have to factor it. If it's not in factor form, I have to factor it. Well, this was an easy one to factor. I factored pretty quickly. I solved for my x's. My zeros, or my x-intercepts, are going to be -1 and 3. So -1, 0 and 3, 0 are my x-intercepts. And again, those are just points on a graph. Solid dots. So next, I have to figure out VAs. Well, what are VAs on graphs? VAs on graphs are when the y values are undefined. Okay, in other words, these are x values that gives me an undefined value for the graph, and that is when I have a number divided by 0. Anytime I get a number divided by 0, that means I used the x that was bad. So this is when the denominator is equal to 0. So I'm going to take my denominator, right here's my denominator, and if I have to factor it. Well, when I factor it, I get something that wasn't that hard, because it's just x squared in front. I get two values for x, -2 and 5. So now I have x equals -2 and x equals 5 as my vertical asymptotes. They're going to be the red dashed lines that I tend to draw in graphs. Now I have horizontal asymptotes. Well, the horizontal asymptote is a little bit different. Horizontal asymptote is when I do leading term over leading term. Now when I write it in standard form, the leading term is the one up front. I'm going to do it shorthand. I'm always going to do LT over LT. The leading term over leading term, when I write it in standard form, are the first terms in both of them. But maybe if I don't write it in standard form, the leading term is always the term that has the highest exponent on x. I made this one pretty easy, that the leading terms are here. So my LT over LT is x squared over x. They kind of cancel out. I get 1. So I get y equals 1 is my HA. So these are the 4 key features that I just did. We did y-intercepts, x-intercepts, VAs, and HAs. But let's talk about all possibilities for HAs right here. Let's say I have a situation where I have, and I'm going to do it just in standard form, where I have a leading term over a leading term, and I have x to an n exponent and b or x to a m exponent in the denominator. And what happens if they are the same degree? So I have an example over here where I have things at the same degree. I do LT over LT. My LT on top is 5x cubed. My LT on the bottom, it's not the first one, it's -2x cubed. So LT over LT is 5x cubed over -2x cubed. The cubes cancel. I get -5 over 2. So I have y equals -5 over 2 as my HA. So in other words, when I have the same degree over the same degree, the x's all cancel out. I'm going to get my HA is y equals some fraction, in this case a over b. If you look over here, it would have been a over b, 5 over -2. What happens if the denominator is a higher degree? Okay, so if you look over here, I have 5x squared over x cubed. So when I do LT over LT, 5x squared over x cubed, I get 5 over x when the x's cancel out. And whenever you have more x's on the bottom, that means you're going to have one of those graphs that we looked at the earlier part of the year. But when you have a higher degree of x in the denominator, y equals 0 will always be the HA. It's always going to level off. Every time you put it in a bigger number for x, 1,000, 10,000, 1,000,000, this fraction is going to get smaller and smaller and smaller. It's going to level off to 0. So whenever the denominator is higher, you're always going to get y equals 0 as your HA. And this last one we're going to do where the numerator is a higher degree. So over here we have these two terms. My LT over LT is 5x cubed over 2x squared. There's more x's on top. I get 5x over 2. Well, 5x over 2 is 2.5 times x. That is a diagonal line that goes up and up forever. There's no horizontal asymptote over here. So when my numerator is higher, you get no horizontal asymptote. So now we're actually going to graph the rational function by putting our dots on the graph for the intercepts and putting our red dashed lines for the horizontal and vertical asymptotes. The first example I'm going to do is what we did on the previous page. So all these 4 key features we already figured out on the previous page. So here are those 4 key features that we figured out on the previous page. Now we're going to draw them on the graph so we can draw the actual graph of the rational function. Okay, so you see I have my x-intercepts, the 2 of them, my y-intercept, and then my asymptotes. And I'm going to do the center part first because I'm going to go through these 3 dots. So it's going to be from negative infinity, x-intercept, x-intercept, y-intercept, x-intercept. So kind of this weird little shape, both ends going down. And then over here, because there's no dots here, there's no x-intercepts on this left part of the graph or this right part of the graph, both graphs have to be level and above going up to infinity next to the asymptote. Level at the ends, going up to infinity next to the vertical asymptote. And that's what that graph looks like from the examples that we did earlier. Okay, next example. Well, I was nice on this next example. I already gave it to you in factored form, so we don't have to factor. So let's go through these 4 details. Okay, so I did all 4 features. Don't forget there's a -3 up front. So step 1, y-intercept, I plugged in x equals 0. Don't forget that -3. I got y equals -2 is the y-intercept. My x-intercept comes from the numerator. -3 doesn't have an x, I don't have to worry about it. So I took my numerator, I found 2 values for x equals -2 and 4. Those are the x-intercepts. My VAs are from the denominator. So I took my denominator, which already factored. I got x equals 3 and -4, the 2 VAs. And I did leading term over leading term. And don't forget about this -3. So the leading term on top would be -3 x, -3x squared. And on the denominator it's x squared. So -3x squared over x squared is just -3. And I'm going to graph these features. So I have all my features graphed. The blue dots are the intercepts, and the VAs and HAs are the red dashed lines. So I'll do the middle part first. So this middle part, to go through these 2 dots, I have to be up at infinity next to this VA, x-intercept, y-intercept down to -infinity. And the right side of the graph I have to be level, but there's a dot to go through, so I'm going to be level going up to infinity next to the VA. And over here, there's no dot. There's no dot here on this x-axis. So I can't go through the x-axis, so I have to be level on the far left and going down to -infinity so I don't cross that x-axis. And there we go. This is what the graph looks like. So here's another problem. Obviously, I cannot deal with this problem in this form. I've got to factor it. If you need help factoring, come see me, but I know it's got to be 2x and x for 2x squared. I'm going to go -4 plus 3 to get my -12 at the end, and then my -5 in the middle. And the one on the bottom is pretty easy. It's an x squared, and it's going to be +4 and -2 to get the -8 of multiplication, and +2 there in the middle. So now I could do my 4 key features. Okay, doing all my 4 key features. The y-intercept, I use x equals 0. I could put it in the factored one, but I put it in the standard form one because these x's all go away. I got -12 over -8, or 3 over 2. Factor in the numerator, set them equal to 0. Hey, a little bit special. I got to subtract 3, divide by 2, so -3 over 2 and 4. My denominator, I got to do -4 and 2, and leading term on top, you can use the standard form. I see 2x squared over x squared, which is y equals 2. So I can draw these on the graph before drawing the final graph. I drew my key features. I'm going to do the in between the two vertical asymptotes. I see these dots here on the x and y axis. I'm going to go from negative infinity through the x and then through the y-intercept like that. Over on the right side, I got to be level, and I see a dot that I can go through right here. So I'm going to be level on the far right and going through the dot down to negative infinity next to the VA. And over here, since I see no x-intercept, I cannot go through that anywhere, so I have to be level on the far left and curve up to positive infinity next to the asymptote. And there we go. That's what the graph kind of looks like. Well, we've been doing equations and graphs. Let's do a graph to an equation. So what do I need? Well, I think we need intercepts and asymptotes, because that's what we've been using so far. That's what we've been plotting so far. So let's see, do I have any intercepts? Let's see, I have an x-intercept here, I have an x-intercept here, I have a y-intercept here. Oops, that's not a y-intercept. I have a y-intercept here. So I have my x-intercepts are equal to -2 and 3. I have my y-intercept equal to 3. And then I have some asymptotes. I have over here I have the VAs at x equals, let's see, I have one here at -1 and another one here at 2. So -1 and 2 are VAs, and I have an HA at y equals, well, it looks like y equals 1 here and y equals 1. But what do I really need? Well, I think when we use our equation, we use x values in our equation. Everything had, the numerator and denominator had x's. So if I did it right now, I would have r of x is equal to, well, -2 becomes x plus 2, and 3 becomes x minus 3, and the v and the x-intercepts are on the top part, over, well, that would be x plus 1, and this would be x minus 2, and the VAs go in the bottom part. So I think right now that's my equation, but I need to check. I really need to need to check my HA. Does my HA work out? Well, my HA is leading term over leading term. My leading term on top would be x and x squared over x and x squared, which is 1. So my HA does check out a 1. So that is my equation for this problem. Now what would happen if my HA was equal to 5 instead of 1? Well, that means my leading term over leading term would have to equal 5. So I think I would have to need a 5 in the numerator. I could spell. So my r of x equation is going to be exactly the same as I had before. X plus 2, x minus 3, x plus 1, x minus 2 in the bottom. But I need a 5. So I'm going to put a 5 right here on top in the numerator. So now when I do leading term over leading term, I get 5x squared over x squared, which is equal to 5, and there's my HA that I wanted. So I think in general, I think what my pattern is, my r of x is equal to, I have x-intercepts on top, I have VAs on the bottom, and if I have to, only if I have to modify it, I threw an HA on in front of the whole problem to get what I want.